We beat LSU though. That was huge. Wasn't that like?
LSU's a joke. Couldn't even score 1 point on Bama. Come on. Chattanooga scored 3 on Bama. All right, so before we get started with catalysis, which will be the 3rd unit of the course, we have 4 more lectures, and then a review, and then the plan is to have the last exam, the final exam. It's not just on this 3rd part, it's on everything. The last day of class, so that we don't have a nice 9-day delay. I know you guys don't want it, I don't want it either. So let's make sure that we stay more or less, yeah.
So we have 3 lectures left?
I'm counting today.
Oh.
We're not done yet. Yeah.
So that final is cumulative. Like there will be.
Yeah, you're gonna have one. You will have a question on catalysis. I guarantee it. So do not flake out on the last 4 lectures. We're gonna decide in a second how many homeworks we're gonna have between now and then. That's up to you. But there's a reason why you might want some.
You're not going.
And yeah, there will be a problem on catalysis. The other 2 problems may or may not deal with catalysis, but they're certainly going to be cumulative in the sense that it's going to be about the stuff that you guys have already learned. All right, homeworks. How many homeworks have we had? 6, right? 7. All right, never mind then. I thought we were at 6. You're going to get 1 more homework, but I'm going to drop 2. So if you're already happy with your homework average, just don't do this last homework, but it's going to be your only time to test your knowledge of catalysis. Yeah.
If we do the 2 homeworks, can it make up for one of the ones that we missed?
No, you're not understanding. There's going to be 1 more homework assignment. It's going to be probably due not this Tuesday, but next Thursday. And because I'm assigning 8 total, we're going to drop 2 over the entire course. Does that make sense? We were already going to drop 1, but since we got to 8, now we'll drop 2. You guys are lucky. I thought we were at 6, so you guys are going to have to ask for a second one to earn a second one. Yeah.
So we actually only have 3 lectures left then? Like today and then
Today, and I think there's 3 more, but
Tuesday,
It would be Tuesday, Thursday. Yeah.
Tuesday, Thursday, and then
Today, Tuesday, Thursday.
And then the exam is
Tuesday. That's it.
There's only 1 more week before that. 1 more full week.
The schedule says today is catalysis, and next Tuesday is catalysis deactivation, and then Thursday's review.
and then
damn, that's it?
then the
I
final-
miscounted.
the final day.
All right, we should be okay, because I mean, we can stick with that timeline. Before we move on, though, and we don't really have time to talk much about it now, but there's a proposal within the faculty to eliminate physical chemistry as a required course. Now let me finish. It would be replaced by a course called thermal physics, which is essentially physical chemistry taught by the physics department.
Yes.
Yeah.
It's a great class.
You learn more.
The difference is,
I mean, we're graduating seniors, so what does it really matter?
well, this is what I'm trying to ask you guys. Slow down a little bit. The differences between the 2 courses, they both teach thermo. Both courses are entirely overlapped with our curriculum, okay? The differences between the 2 courses is one's a 4-hour course, one's a 3-hour course, and we need to find an hour. The other difference between the 2 lectures is physical chemistry teaches kinetics. So the question that I want from you guys, send me an email, come up to me after class, anything, any way you want to voice your opinion. How much did the kinetics portion of PChem prep you for this class or not at all? That's what I'm asking about. Not right now, not right now. Shoot me emails, come up to me anytime. But I want feedback from you guys about how important was that section of that course, because that's the part we're going to be losing if we go through this proposal. And so the next kineticist joining the group, joining the class will not have had that background. So I wanted to know if it was a useful background or not. I didn't even know you guys had it. So I taught as if you didn't have it. But overlap is not always a bad thing.
Assume no background.
Oh, I will continue to assume no background. It's just a question of whether it helped you to have that background. So again, let me know. Either way, the course is not long for this earth because it's entirely overlapped. So we want to do something with it. We're just not sure what. All right, so again, since now I've seen the syllabus for PChem, you guys have evidently had this topic before, at least in a very short way.
Oh, yeah.
We're going to be talking about catalytic reactions, and I think the first thing to kind of talk about is how many steps are involved in a catalytic reaction. And so we're going from A to B, and we're only going to have one actual catalyzed step, as you're going to see in a second. But there's other processes that have to take place. So here's my gas phase A and my gas phase B, and here's my surface of my catalyst. And I'm just noting here that it's the active part of my catalyst. Catalysts are often made of an active species supported on a roughly inert material. And that's so that we don't have to use 10 grams of platinum. We use a tiny amount of platinum and we put it on something cheap like silica or aluminum. So this is my active phase. So is there anything that has to happen? What are the steps that has to happen in order to get this from the gas to my active phase? Yeah.
A and B have to travel towards the surface.
Yes. And when they do that, is it a...
Diffusion.
It's diffusion. And then what's the last step of that called? Adsorption. So let's start with adsorption. So here we're going to have A star.
Are we assuming this is their surface?
Yeah, sure.
Okay.
For the picture that we're putting up here. So we have A star, and so what does the star mean? It's adsorbed. Yeah, we're not using the star like we did in the first part of class, where we meant that it was activated. The other way that we're going to write this, because the book writes it this way, so I'll write it this way at least a few times, is like that, A dot S, because S in Vogler indicates an active site. That's where he gets the S from, so think site. I think he was worried that people would forget that stars also matter. Okay, so we have A star, and it reacts to form what? B star. And so someone mentioned that there's an adsorption step. And I'm going to call this A near. Because it's A near the active site of the material. Is there any other step between the gas phase and A near? We normally split this actually into two steps. So let's put a picture out here and say that we have a catalyst particle. So this is a supported particle. So what is roughly the size of a supported catalyst particle? Give me a unit. Is this a meter? Is it a nanometer?
Say something like
On the order of microns. This is something you can see. It looks roughly like a grain of sand. And now sometimes you'll actually bind these together into things that are even larger. But the material itself, the support, usually has a size of around a few microns from that range. So again, that's not where the active material is. The active material is inside that support. So this is not a solid surface. This is a porous material. And within this porous material is where you're going to have, hard to see, but a little dot. That would represent your active site. This isn't always the case, but this is very commonly the case that a catalyst is made of an expensive active material that's supported on an inexpensive support. So the first thing that we are going to do is diffuse A from here to here, just outside the porous region of the support. And so this is diffusion that can be characterized through simple bulk diffusion techniques that you guys have already learned. This is no different from diffusing in a pipe or something. This is just bulk phase diffusion. And then from the pore of the support of the catalyst to the active site, we have more diffusion, but now this diffusion is on a very different length scale. So this is intraporous And so you first diffuse from the bulk region to the pore entrance of your catalyst particle, and then from the pore entrance to the active site of your catalyst. And then this last step is adsorption, which is when it binds to the surface of your catalyst. And then we react, and then we have the same thing over here. So what are the diameters of those pores that you have to diffuse through once you reach your catalyst particle? Yeah, this is the nanometer range. This can even be the sub-nanometer range. So you're going to be talking about nanometers to angstroms range, depending on the type of support.
Is that an entry and an exit point?
Yeah, I mean, yeah, right. I mean, they are porous, so technically you can go in one pore and out the other, but you can, yeah, there's diffusion happening in both directions.